Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 3, Projectivities of the Primitive Geometric Forms of 1, 2, and 3 Dimensions. Section 27, Group Properties of Projectivities. From the definition of a projectivity between one-dimensional forms follows at once Theorem 7, the inverse of any projectivity and the resultant of any two projectivities are projectivities. On the other hand, we notice that the resultant of two perspectivities is not, in general, a perspectivity. If, however, two perspectivities connect three concurrent lines, as in Theorem 3, their resultant is a perspectivity. A perspectivity is its own inverse, and is therefore reflexive. As an example of the general principle of Section 26, we have the important result. Theorem 8. The set of all projectivities leaving a given pencil of points invariant form a group. If the number of points in such a pencil is unlimited, the group contains an unlimited number of projectivities. It is called the general projective group on the line. Likewise, the set of all projectivities on a line leaving the figure formed by three distinct points invariant forms a subgroup of the general group on the line. If we assume that each permutation, chiefly theorem 1', of the 3 points gives rise to only a single projectivity, the proof of which requires an additional assumption, this subgroup consists of 6 projectivities, including, of course, the identity. Again, the set of all projectivities on a line leaving each of 2 given distinct points invariant forms a subgroup of the general group. We will close this section with 2 examples illustrative of the principles now under discussion, in which the projectivities in question are given by explicit constructions. Example 1. A group of projectivities leaving each of 2 given points invariant. Let M and N be 2 distinct points on a line L, and let M and N be any 2 lines through M and N respectively and coplanar with L. Figure 27. On M, let there be an arbitrary given point S. If S1 is any other point on M, and not on L or N, the points S, S1, together with the line N, define a projectivity pi1 on L as follows. The point pi1 of A is equal to A prime, homologous to any point A of L, is obtained by the 2 perspectivities. The pencil A is perspective with center S to the pencil A1, perspective with center S1 to the pencil A prime, where A1 is the pencil of points on N. Every point Si, then, if not on L or N, defines a unique projectivity pi sub I. We are to show that the set of all these projectivities pi sub I forms a group. We show first that the product of any 2, pi sub 1, pi sub 2, is a uniquely determined projectivity pi sub 3 of the set. Figure 27. In the figure, A prime is equal to pi sub 1 of A, and A double prime is equal to pi sub 2 of A prime have been constructed. The point S3 giving A double prime directly from A by a similar construction is then uniquely determined as the intersection of the lines A double prime A1 and M. Let B be any other point of L distinct from M and N, and let B prime be equal to pi sub 1 of B, and B double prime equal to pi sub 2 of B prime, be constructed. We must show that we have B double prime is equal to pi sub 3 of B. We recognize the quadrangular set Q of M B prime A prime, comma, and A double prime B double prime as defined by the quadrangle S S2 B2 A2. But of this quadrangular set, all points except B double prime are also obtained from the quadrangle S1 S3 B1 A1, whence the line S3 B1 determines the point B double prime. Theorem 3 of Chapter 2. It is necessary, further, to show that the inverse of any projectivity in the set is in the set. For this purpose, we need simply determine S sub 2 as the intersection of the line A2 with M, and repeat the former argument. This is left as an exercise. Finally, the identity is in the set since it is pi sub 1 when S sub 1 is equal to S. It is to be noted that in this example the points M and N are double points of each projectivity in the group, and also that if P, P', and Q, Q' are any two pairs of homologous points of the projectivity, we have Q of MPQ, and Q', P'. Moreover, it is clear that any projectivity of the group is uniquely determined by a pair of homologous elements, and that there exists a projectivity which will transform any point A of L into any other point B of L, provided only that A and B are distinct from M and N. By virtue of the latter property, the group is said to be transitive. Example 2, commutative projectivities. Let M be a point of a line L, and let M be any two lines through M distinct from L, but in the same plane with L, figure 28. Let S be a given point of M, and let a projectivity pi sub 1 be defined by another point S1 of M, which determines the perspectivities. The pencil A is perspective through S with the pencil A1, which is perspective through S1 to the pencil A', where A1 is the pencil of points on M'. Any two projectivities defined in this way by points S sub I are commutative. Let pi sub 2 be another such projectivity, and construct the points A' equal to pi sub 1 of A double prime equal to pi sub 2 of A', and A1' equal to pi sub 2 of A. The quadrangle S, S2, A1, A2 gives Q of M, A', M, A double prime, A1', and the quadrangular set determined on L by the quadrangle S, S1, A1, A2' has the first 5 points of the former in the same positions in the symbols. Hence we have pi sub 1 of A1' equal to A double prime, and therefore pi sub 1, pi sub 2 is equal to pi sub 2, pi sub 1. Exercises 1. Show that the set of all projectivities pi sub I of example 2 above forms a group, which is then a commutative group. 2. Show that the projectivity pi sub 1 of example 1 above is identical with the projectivity obtained by choosing any other 2 points of M as centers of perspectivity, provided only that the two projectivities have one homologous pair, distinct from M or N, in common. Investigate the general question as to how far the construction may be modified so as still to preserve the proposition that the projectivities are determined by the double points M, N, and one pair of homologous elements. 3. Discuss the same general question for the projectivities of example 2. 4. Apply the method of example 2 to the projectivities of example 1. Why does it fail to show that any two of the latter are commutative? State the space and the plane duals of the two examples. 5. A, B, C, D is a tetrahedron, and alpha, beta, gamma, delta, the faces not containing A, B, C, D, respectively. And L is any line not meeting an edge. The planes LA, LB, LC, LD are projective with the points L alpha, L beta, L gamma, L delta. 6. On each of the 10 sides of a complete 5-point in a plane, there are 3 diagonal points and 2 vertices. Write down the projectivities among these 10 sets of 5 points each.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.